All right, we're not gonna bother with the first one. That's too easy. Let's try second one. It says find the second derivative, okay, not the first. So we want to find f double prime of x. In order to get the second derivative, you need to find the first derivative. All right, what's f prime of x? How do we do
You
this?
bring the 3 in the front and then
Yeah,
everything to the power of 2.
is that it? Are we done?
You have to do the inside of the bracket.
So what is the inside? What is the derivative of the inside?
2.
Yeah, it is. So that's just 6 times 2x minus 5 squared. This is the first derivative. Now let's go deeper, one level. How do we find the derivative of this guy? It's the same idea, right?
You bring the 2 in the front.
Yeah, so that'll be 12, and then this thing stays as it is to the power of 1. What do we multiply this by?
2.
Yes, so it's going to be 24 times 2x minus 5. You can open that bracket if you want, 120, and you're done. Easy as that.
Mm-hmm.
Okay, what about if I give you a quotient rule problem? Numerator is f, denominator is g. Quotient rule says f g prime minus f, f prime g minus f g prime all over g squared. What's f prime?
1.
No. 1 would be if it was x, it would be 1.
So it's 15.
No. Number disappears. It's 0. The derivative of a number is 0.
Oh, okay.
So you have 0 times x plus 3, right? So that's just 0 minus 15 as it is times the derivative of the bracket. What's the derivative of x plus 3?
It's 1.
It's 1, right? All over the denominator squared as it is. So x plus 3 squared like that. If you clean this up, you'll get negative 15. Y prime will be negative 15 over x plus 3 squared. Now we have to go a level deeper though. Now let's do the same thing again. What's f prime? If f is 15, negative 15, what's f prime?
0.
Yeah, exactly. So 0 times x plus 3 squared, that's still a 0, minus the for top guy as it is. What's g prime?
You bring the 2 in the front.
Mm-hmm. Everything inside stays as it is. Do we need to multiply that by anything?
By just 1.
Yeah. All over what? The denominator squared, right? So basically you have x plus 3 squared, and then you have to square this again. What does that give you?
To
It's
the power of 4.
yeah, exactly. So x plus 3 to the power of 4. If you want to clean this up, look at this. Negative becomes a positive 15. 15 times 2 is 30, so you have 30 times x plus 3 over x plus 3 to the power of 4. And one of the x plus 3's cancels out with one of the x plus 3's in the bottom. So you'll get 30 over x plus 3 to the power of 3. And you are done. Okay?
Okay.
So that's the double derivative, I guess, using the quotient rule. And remember the triple thing that we did? Displacement, also known as position. If you take the derivative of position, you get velocity. If you take the derivative of velocity, you get acceleration. Displacement is the distance. Actually, the displacement is not the distance. It's I guess logically it's similar, but I'll tell you what displacement is technically what exactly is displacement. Let's say you start here, yeah? Let's say you travel to point A. Let's say this is O. Let's say you travel to point A. This is 1 kilometers. From here you travel to B, which is 2 kilometers. And then you travel down to C. Let's say that's also 2 kilometers. Yeah? Your distance, the distance that you traveled is gonna be 1 plus 2 plus 2, 5 kilometers. Okay? Distance is 5 kilometers. But displacement doesn't care about the direction. Displacement is the distance that you traveled from your very first starting point to where you ended up, right? So we started here and we ended up right back here. Your displacement is what? 0. So that's what displacement is. Cool? Displacement only cares about your initial and your final position. It doesn't care about the directions that you took. Similarly, let's say that you walk at, I don't know, like 1 kilometer per hour, okay? So your speed is gonna be distance over not speed, sorry. Am I looking for speed? Let's say this trip took you 2 hours, okay? Going from here all the way here. So your speed will be distance divided by time. So it's going to be 5 over 2 kilometers per hour. That's your speed. But your velocity is going to be your displacement divided by the time. Displacement is 0, time is 2, your velocity is 0. That's the difference between displacement and distance. And yeah, that's it. The idea comes from something known as vectors, which are just like normal letters with a little direction arrow on top. What does that even mean? Vector is a quantity that has both a magnitude as well as a direction. Whereas a scalar quantity strictly only has a magnitude, okay? An example would be like 2 kilometers per hour is your speed, but if you say 2 kilometers per hour east, then that would be your velocity, which is a vector quantity, needs a direction, you need to specify a direction, whereas for a scalar quantity, you don't. Everything here, displacement, velocity, acceleration, they're all vector quantities. They all have a certain direction, which we won't go into super deep here, if at all, but that'll come into play if you take physics, when you get to your physics thing, in your science class. What are you doing in science?
Chemistry.
How's that?
It's okay.
Name me an acid.
We haven't learned acids yet.
Second element on the periodic table.
We don't memorize the elements on the periodic table.
Any element. Anything. What's water made of? It's made of 2
Hydrogen
elements. Yeah, hydrogen.
and
What's the other one?
oxygen.
Yep, that's right. I mean, if you want to really see what a water molecule looks like, oxygen is the 8th molecule on the periodic table, okay? What does that mean? It means this. Here, let's just kind of quickly go on a tangent here for a very brief period. Oxygen is the 8th element. It means it has 2 shells. The first shell can only take 2 electrons, okay? 8th element means it has 8 electrons. So in the second shell, it has 6, 3, 4, 5, 6. I'm going to show you why H2O is water. Why not HO, right? Why is it H2O? So if you look at an oxygen molecule, this is oxygen. You see these 6 electrons? You need to draw them out here. 1, 2, 3, 4, 5, 6, okay?
Uh-huh.
It needs 8. It needs 8 for it to be full, for it to be stable. If it doesn't have 8, it probably doesn't exist nor in normal circumstances. If you look at hydrogen, it has 1. It only has 1 molecule. So hydrogen needs 1 more. Okay, hydrogen needs 1 more. You can either have 2 or you can have 8. Hydrogen is in the first shell, so it needs 2. It's lacking 1. Oxygen is in the second shell. It's lacking 2. So what happens is that you see this hydrogen electron, this one and this one pairs up. This one and this one pairs up.
And then it's a compound.
Yeah, exactly. So hydrogen is satisfied now because it needs 2, it has 2. Oxygen satisfies, it needs 8. It has 8. 1, 2, 3, 4, 5, 6, 7. So everything is good here. So that's why water is H2O. Chemistry is pretty fun, especially the labs. Well, I guess you don't, do you do like practical things in science? Like in the
Like what?
biology class, did you like look at a worm or something in real life? I don't know. I don't know what they do these days.
No.
Okay.
We did that in like grade 8 though.
Okay. So here, let's look at this question. They've given us some position equation. Cubic, right? Cubic equation. Calculate the displacement at 3 seconds. What do we do? Do we need to find the derivative for A?
No.
No, you don't. All you do is you find S of 3. So it's going to become 3 cubed minus 21 times 3 squared plus 90 times 3. So 27 minus 21 times 9 plus 90 times 3. That is 108. What's the unit of displacement? It's the unit of distance, right? Length, meters. B, calculate the velocity at 5 seconds. What do we do now?
You find the derivative.
Okay, what would that be? It's pretty simple, right? T cubed, 3 is going to come in the front. Going to become
T squared.
yeah, and then what about the next one?
The 2 comes in the front.
That becomes 42t. The last one, what about the last? What's the
You
derivative
get
of?
left with 90.
Yeah, that's it. Left with 90, that's it. And then they want at 5 seconds, and now you're going to find S prime of 5. So 3 times 5 squared minus 42 times 5 plus 90, like that. So 3 times 5 squared minus 42 times 5 plus 90 minus 45. 10 points if you can tell me the unit of velocity. It's the same as unit of speed. Velocity is the same as speed.
Is it meters per second?
Yeah, it is meters per second. And it comes from this because velocity is the slope of displacement. Just imagine displacement, you have meters on the y-axis, you have time on the x-axis. So when you find the slope, it's going to be rise over run. Rise has a unit of meters, run has a unit of seconds, meters per second. C, calculate the acceleration at 4 seconds. That means we need to find S double prime of t. What would that be if this S of t is given up there? We found earlier.
Six T minus 42.
Yeah, 6 minus 42, and then they want it at 4 seconds, so then we got to find S prime of 4. 6 times 4 minus 42, 24 minus 42, negative 18. Okay, 20 points for the unit of acceleration. I'm going to give you a hint. Acceleration is a slope of velocity graph. On the velocity graph, you have meters per second on the y-axis. You have seconds on the x-axis. So you do rise over run, right? You do meters per second divided by second. What does that give? Meters per second divided by seconds. Meters per second times 1 over seconds. So division turns into a multiplication. A little bit of flippity action for the second guy. M over s squared, and you're done. Meters per second squared is the unit of acceleration. Cool.
Mm-hmm.
That is also the unit of gravity. Okay, so here, does gravity exist?
Yes.
Okay, so why is it just called the theory of gravity? What does that mean? Does it mean it's unproven? Does it mean it's just an idea? Theory of gravity.
Isn't like a theory something that is like continuously tested?
Yeah, it is. So that's where the distinction comes into play. When you're watching a whodunit film, right? Your friend is always like, "Oh, I have a theory about who the killer could be," right? This is from a casual sense, a theory. Whereas from a scientific point of view, a theory is something that's been tried and tested multiple times. This theory that you think in real life, the casual sense, it's not the same thing as this. A lot of people, that's why you see even today, every day, you just look it up on YouTube, like everyone's calling gravity just a theory, it doesn't exist, yada yada. No, that's they have not made the distinction between the casual word of the use and the scientific word. It definitely exists. Gravity definitely does. Um, like it's weird, like we're trying to find a new particle. I don't know how much progress we've made, but like magnets, how they work. Magnets have something called a magnetic field. Let's say this is a magnet, it is South Pole, North Pole. It has something called a magnetic field, okay? It looks something like that. It's invisible though, obviously it's invisible. So these arrows are vector arrows. They are called field lines. So that is what pulls one magnet to the other, or like a metal to a magnet, right? So we are actually trying to find something like this when it comes to gravity, because something is definitely pulling it down, right?
Mm-hmm.
But we don't know exactly what is pulling us down. We're trying to find like a particle maybe, or I don't know, something like those field lines for magnets. If we do, I don't know what that would really mean. I guess it would just prove, it will even give more credit to gravity, which it already has enough, but okay. The question, this is the same thing. Actually, this is not the same thing. A ball is thrown upwards. Its motion is described by this quadratic. It's a parabola. Opening up or down?
Down.
What's the y-intercept?
Is it 2?
Yeah, it is. So we don't know where the vertex is, but we're going to find it soon. So it's going to look something like this. This is the graph of displacement or height, I guess. Height is on the y-axis. The unit is meters. And time is on the x-axis. The unit is seconds. What's so important about this turning point? What happens at the turning point? Something
Slope
is,
is 0.
yeah, if the slope is 0, what does that mean? What is 0? What's the slope of a displacement graph? Displacement, the slope is velocity, right? Speed. And
Mm-hmm.
the slope of a velocity graph would be acceleration, okay? So determine the initial velocity. What do we do? They've given us, again, height is a displacement function. Keep that in mind. Anything lengthwise, it's going to be a displacement function. How do we go about doing A?
You find the derivative.
Yep. Well, what would that be? So h prime of t would be negative 9.8 t plus 6, right? Okay, it says initial velocity. What does that mean? What's the time initial?
T is 0.
Yeah, exactly. T is 0, boom, gone. So the answer is simply 6 meters per second. Notice how it's positive. That means it's going up, and we know it was going up because right now when time is 0, it's going up, the slope is positive. B, when does the ball reach its maximum height?
You find the second derivative?
No. Second derivative has to do with acceleration. Maximum height is right here. Look at the in the displacement time graph. You see maximum height? What happens at the max height? There's a turning point, right? Slope is 0. So what you need to do is you need to set h prime of t equals to 0 and solve for t. So basically you just set this as 0, the slope function is 0, right? And then you solve for t. And if you get a negative time, you probably did something wrong. To solve for t here, subtract 6 from both sides, divide by negative 9.8, and that's going to give you a positive answer. So negative 6 divided by negative 9.8. You can cancel out the negative signs if you want. 0.61 seconds. Cool? Does that make sense? C, when does the ball hit the ground? There's two ways to do this. You can use the quadratic formula to find the x-intercept. I guess that's the only way to do this. When does the ball hit the ground? Yep, that is the only way to do this, unfortunately. I was trying to be cheeky, but it doesn't work for this question. What I meant was this, the maximum value, yeah?
Mhm.
See this? This point is always going to be the midpoint of this and this. So if it passed through the origin, and if you know where this is, if this was 0.6, then this must be 1.2 because it's symmetrical, right? Whatever is here must be here. So I was trying to be smart there, but it's not going to work out because this does not go through the origin. So you actually have to use the quadratic formula to find the x-intercept. You can't man this because there's decimals in there when you find, there's no point. Do you remember what the quadratic formula looks like? Any part of it? It has like an ABC component on it. Looks like this. And you're going to see this a lot. Like that. What's B? Again, it's always going to be in this form, right? Like bx plus c. Any quadratic is always in this form. Compare this guy with this guy. What is B?
6.
Yeah, so minus B. So minus 6 plus minus 6 squared. What is A?
Negative 4.9.
Yeah, negative 4.9. What's C?
2.
2. Divided by 2 times negative 4.9. Yeah, like that. So this gives you negative 4 plus minus. I guess I can just do the square root thing. Square root of 6 squared minus 4 times negative 4.9 times 2. That gives me 8.67 over 2 times that would be negative 9.8. So it's going to give me two different values. Negative 6 minus 8.67 divided by negative 9.8. One of the answers is 1.50 seconds. The other one is 6.87 divided by negative 9.8. So basically, you do this twice, right? What does the plus minus mean? So you either do this guy, the plus bit, that'll give you negative 0.27 seconds, or you do the minus bit, which gives you this one. What's the answer here? 1.5 or negative 0.27? Only one of them is right. The question was, when does the ball hit the ground? To do that, we found the x-intercept. So we were looking at this.
It's 1.5.
Yeah. It can't be negative 0.27 because time will never be negative, right?
Mhm.
Time will, that value is actually this here. You must be wondering like, okay, wait a second. It does exist because it's on the graph. No, we're using a quadratic equation to model a real life scenario, right? This is just a modeling technique, so we could have completely ignored anything in the negative quadrants. also on the y quadrant, because unless he was throwing it in water or something, there's no way the ball or whatever goes through the ground. It's not gonna go to China, right? Because eventually it will, but there's a ground there, it's probably gonna bounce. It's actually, technically, it's gonna look like this. The motion of the ball, let's say this is the hill, someone's gonna toss it up, it's gonna come down, and then it's gonna repeat. And then it's gonna repeat, and then eventually it'll just roll. That would be a more realistic thing. But don't worry about that. You actually do need to do this, not at this level, not even close, but eventually, years later, you're gonna deduce exactly what these are as well. This is something called dampening. Used in real life situations such as a spring, because spring follows this as well, right? Like if you let go of a spring, it's gonna do zigzag, zigzag, but eventually it's gonna stop. It's gonna do less, 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 and it's gonna stop like that. Another super useful real life application of this idea is earthquakes. When you're building a building or a bridge or anything, you got to take that into account. Like how much can a bridge swing before it collapses? So that's definitely something that people do take into account. And also people do not take into account. It has happened many, many, many times where because of a strong wind or an earthquake or something, the bridge just collapses. It can only bounce around so much, right?
Mhm.
Anything solid is elastic. I don't know if that makes any sense. Like, even if you have a solid piece of a pen, we might need that answer. The answer is 1.5. Even if you have a solid piece of a pen, if you swing it, like if you would just use a hand, it's gonna give you like a nice elastic motion like that, yeah? If you swing it up and down, at some point it's
Uh-huh.
gonna look like this. So anything solid, anything rigid is also elastic. That's where earthquakes happen, actually. Like, how do earthquakes happen? Give me some ideas on what's the idea behind earthquakes?
The tectonic plates like move over each other.
Yeah, exactly. So the tectonic plates are something like this, right? Like, they're not like completely rectangular like this. I guess like that. One of them is here, the other one is here. What happens is over time they're gonna keep moving, and at this point they've stored a lot of elastic energy in them. And once that gets released, then we feel the effect, I guess, the energy. Um, cool. So that was the answer to D. It's gonna hit the ground after 1.5 seconds, not 0.27 negative. That's invalid. Okay, what is the acceleration of the ball on the way up? Now what do they want? They want acceleration, right?
Did we do D yet?
Yeah, no, actually we did not. Let's do D. No, we did C. C was 1.50 seconds. D, what's the velocity when it hits the ground? We know it's gonna hit the ground after 1.5 seconds, right? So all you
Mhm.
do is you find h prime of 1.5 because that's our velocity function. So negative 9.8 times 1.5 plus 6. So negative 9.8 times 1.5 plus 6. So that gives you negative 8.7 meters per second. Does it make sense that the slope here is negative?
No.
Yes, it does though, because if you look at it, it's going down. If you draw a tangent line there, this is the ground, right? If you draw a tangent line here, look at the line. It's a negative slope. So it does make sense that its velocity is negative. Negative velocity just means it's coming down, right?
Okay.
It doesn't mean it's going back, because that wouldn't make sense. Not without some sort of like an external force, because that would violate laws of motion. Have you done that?
No.
Okay, you will. This comes from a scientist back in the 19th century known as Newton. This is the Apple guy, the gravity guy, right? If you know the story, is one day, I don't know how true this is, but this is the myth. He was just chilling here, sitting, next to an apple tree, and then randomly an apple falls down onto the ground. And he was like, why? And that's how we know today as gravity. But he's known for a lot of things. He's known for something called his laws of motion, which is basically that's something that allowed us to go to the moon. There's three of them. The most, I guess they're all kind of important, but the most important is this. Every action, yeah, whatever you do, every action has an equal but opposite reaction. So what does that mean? If you bang your pen on the table is going to bang you back. If you punch a wall, the wall will punch you back. That's how you feel pain, I guess, in your hand. Whatever you do, something else is also going to happen, whether you realize it or not. But that's not what explains the going back thing. This is the third law. What explains is the first law, which basically says everything is gonna continue whatever it's doing, okay? If it's just sitting still, it's gonna sit. If it's standing, it's gonna stand. If it's moving, it's gonna move. Everything's gonna continue its motion unless you apply external force. Right? A car, how does a car come to a stop? It's because you're applying the brakes, right?
Mm-hmm.
If you didn't apply the brakes, it's gonna keep moving. Like, yeah, why is the book on the table? Well, it was there to begin with. Unless you move it, it's gonna stay there. So that's what this is. So the ball is coming down. Unless someone kicks it or unless like there's a strong gust of wind, there's no way it's gonna go back up. Anyways, the point here was negative velocity means it's coming down. The negative sign is just a direction. Because it's a vector quantity, it's a direction. So that's the answer to D. E, what's the acceleration of the ball on the way up? So what's the idea behind this one? How do you find the acceleration? It's the double derivative, right?
Mm-hmm.
We have the first derivative up here. H prime of t was negative 9.8 t plus 6. So what's going to be h double prime of t?
Negative 9.8.
Yes. Does this change depending on whether it goes up or down? Notice how this one doesn't care about time. It's independent of, there's no t variable in it, right? It's independent of time. Yeah?
Uh-huh.
So what does that mean? How does that work? You see this negative 9.8? This is actually a very important number. This is the Newton's numbers that we were talking about earlier. This is g. This is gravity. Technically, the thing is called acceleration due to gravity. And this is constant. This is the rate of change of speed on Earth, basically, negative 9.8. This is how fast something drops. On the everything, yeah, basically, everything is being pulled towards the Earth's core at an acceleration of 9.8 meters per second squared. Everything. Just because it's being pulled doesn't mean it's going to get sucked into the Earth. Okay, basically, yeah, to the ground. I guess you can think about it, to the ground. Anything that's not on the ground, it's being pulled.
Why does it just stop at the ground?
Why does it stop at the ground? No, it doesn't stop at the ground. It's going to go all over the crust. It's because we can't penetrate the ground. The force is not strong enough. It's not a super strong magnetic force or anything. And the negative 9.8 is mundane, actually. And this depends on so G on Earth is 9.8. It's a negative. Negative just means it's coming down, pulling it towards the center. On the moon, I think it's about 1.6 or something. It's definitely way less than Earth. right?
Mm-hmm.
So what does this mean? This means on the moon, this is the rate at which it pulls you down, right? The force at which it's pulling you down. On the moon, you can jump way higher than Earth. You've probably seen like if you've ever seen like a moon video, you can see the astronauts kind of jumping. You can jump way higher. On Jupiter, Jupiter, I don't think you can even jump. Yeah, there's no way we can even jump. It's so high. Actually, let's look this up. G values, right? So 9.8 is not that bad, right? 9.8 is what we're used to on the Earth. So Mercury, it's a pretty small planet, yeah.
Mm-hmm.
And if you look at the radius, it's like yeah, it's pretty small. Venus is almost 9.8. Mars is 3.7. Look at Jupiter, 26. But Pluto seems fun though, 0.61. This you can really jump like house high. Definitely. You can jump basically, what is this? 9.8 divided by 60.61. You can jump 16 times higher. Oh my God. Imagine that. Pluto. Poor Pluto. Anyways. Why is Pluto not a planet? I think we've talked about this before. Why did they get kicked out of the whole planetary system? You know that it did, right? How many planets are there in the solar system? There used to be 9, but now there's 8.
Because Pluto's just like gas or something.
The gas is Jupiter is actually all gas. Jupiter and Uranus, they're both gases. In fact, the pressure is so high. Jupiter is legit all gases. It doesn't even have like a solid core, but it does. It's because the gas has solidified. Everything on Jupiter is all made up of gases. That's like they don't have like rocks or anything like that. That's what I meant. There's no soil,
Mm-hmm.
there's nothing of that sort. It's all gas that has been solidified basically because of the high pressure. If you jump into Jupiter's orbit, you're gonna die very, very quickly. Um, Theoretically, if you jump in from this side, if you throw like a fridge or something, it should come out of the other side. We thought this was gonna be the case before because it's all gas, right? It doesn't have like a solid core like Earth, but turns out it does have a solid core. We found that out later. This is all like solid, like CO2 and whatnot, H2. Jupiter is pretty interesting. No, Pluto was not a planet because it didn't meet the definition of a planet where you need to have consistent orbits around the sun. Like you've probably seen like a model, right? Like, see, this is the sun.
Uh-huh.
Let's say this is sun. This is gonna be Mercury, Venus, like that, Earth. The orbit is relatively stable, right? We're gonna do this throughout. But what happened with Pluto was that this is the sun, yeah. What happened with Pluto was that one time I was doing this, and then the next time I was like doing this, and the next time I was like doing this. The orbits were not constant, so it didn't meet the definition of a planet. Something that does this is more like an asteroid. Okay, so it fits more the definition. Technically, it's more of an asteroid than it is a planet. It needs to be stable in its orbit around the sun. That's why Pluto got kicked out about 20 years ago. It was a sad day. All right, what else can we do? Okay, it says find the maximum and the minimum values. Let's do this for this one. Max and min, right? Again, remember what happens at a maximum and a minimum. See, like this is the maximum value. What happens here? What's going on? What's so special about this point?
The slope is 0.
Yeah, exactly. The slope is 0. So let's first find the slope, and then we can see what is 0. What's f prime of x?
You just bring a 2 in the front.
That's it. It's going to be 2x plus 4 because it's 2x plus 2, open the bracket, 2x plus 4. And then you're going to set this equal to 0. You get 2x plus 4 equals to 0. What's x? If 2x plus 4 is 0, what is x?
-2.
-2. Now the question is this a maximum or is it a minimum?
A minimum.
Nice. How do you know?
It's negative.
Oh, no, that has nothing to do with that. It's minimum because this is a quadratic that opens upwards. It must have a minimum, right? But it could definitely also be like a local maximum here. Check this out. If you have something like this, you see a -2, it could definitely be, or even like an absolute maximum. So negative doesn't mean it's a minimum, okay?
Okay.
But what if you don't know what the graph looks like, right? What if you don't know what the graph looks like? So when you plug -2 in there, you get a 0, yeah? And you want to plug any other number in the interval in there. Now I'm going to plug 3 in there. So 3 plus 2 squared, that's 25. Notice how 0 is less than 25? It must be a minimum. So you use a test point. This thing is called a test point. You just compare it with something else. If you don't know what the graph looks like, more often than not, you won't. You'll have an idea, especially if it's a polynomial, then yeah, you can like kind of do a rough sketch, but if not, then not. Like look at let's do the next question because this one's okay. What about this funky looking thing? How do you find f prime of this? You can use a trick to make your life way easier. Use a trick so that you don't have to use the quotient rule. The trick is
You bring
this.
your x's.
Yeah, this becomes -1, that becomes -3. This is still f of x. Let's find f prime of x. What do we get?
-1.
Negative x to the power of what?
Oh, -2.
Yeah, -2 minus -3, x to the power of -4, yeah? I'm going to toss that in the denominator. -1 over x squared. Then this becomes plus 3 over x4, like that. Okay? Now this is where it gets a little bit difficult. We have to set this equal to 0 and solve for x. What is the LCD between x squared and x4?
Is it x4?
Yeah, it is. Yeah, that's perfect. It is x4. What do we need to multiply the x squares by?
x2?
Yep. So look at this. You get -x2 plus 3 all over x4 is equal to 0, right? What do we do next? We're trying to solve for x.
You subtract 3?
No, you can't.
Oh, you have to multiply by x to the power 4?
Yeah, you have to multiply. You multiply 0 times x4, that just disappears. And then you subtract 3. So you have -3 is -x squares. The negatives cancel out. So x is going to be plus minus the square root of 3, okay? Plus minus. So let's check for minus root 3, and then we'll also check for plus root 3. So 1 over minus root 3 minus 1 over, okay, this is going to be annoying. Minus root 3 cubed. I'm going to plug this in a calculator. 1 divided by minus root 3 minus 1 divided by minus root 3 to the power of 3. So that gives me negative 0.38, okay? Now we're going to do the same thing for the plus root 3. 1 divided by plus root 3 minus 1 divided by root 3 cubed. That gives me positive 0.38. So negative gave me negative 0.38, plus root 3 gives me 0.38. So which one's the max, which one's the min? So these are your points, right? Negative root 3, negative 0.38. That must be a minimum, right? Look at the y value. It's negative 0.38. Whereas for the positive root 3, we got a positive 0.38. So that must be its maximum. Okay. So root 3 is the max. When x is root 3, you get a maximum. When x is negative root 3, you get a minimum of this function. Yeah, look at this. This is what we were talking about earlier. On the surface of the moon, astronaut can jump higher because the force of gravity is less than it is on Earth. When someone jumps, his height is modeled by this. What is the acceleration due to gravity on the moon? Alrighty, what's the idea behind this one? Any ideas? I know you know how to do this. I mean, we've talked about how to do this. I don't know. They've given us S, which is a displacement, right? How do we get acceleration from displacement?
Double derivative?
Yep. How do we go about finding the double derivative of this? You could use product rule, right? But you don't have to. What happens if we open the bracket? Let's just straight up open the bracket. It'll make our life easier. If you toss the 3 in there, what do we get? The t in there, sorry, not t. 3. No? You gotta FOIL this, right? Like t goes with negative 5 over 6. You get negative 5 over 6 t squared. And then t is also gonna go with 1. T times 1 is a t. No, it did. Any issues with the foiling?
No.
Now let's find the first derivative, which is gonna give us the velocity, right? What would that be here? The first derivative.
You bring the 2 in the front?
Yep, so you get negative 10 over 6 t plus, what's the derivative of t?
1.
Yep, that's the velocity. The next one is acceleration. What would that be? S double prime of t. What is that?
Negative 10 over 6.
Yeah, negative 10 over 6, which is like 1.55, right? Compared to Earth, Earth is 9.8, the moon is 1.55. So you can jump, well, I don't know if that's 6 times higher, which would be kind of cool, right? So basically the entirety of moon is a trampoline. It's a giant trampoline. This also dictates how big like people can be though. Like 9.8 is average, right? If moon had a life, their people would probably be taller because they're not being pulled as much as we are. Yeah.
Uh-huh.
Whereas if Jupiter had people, obviously they don't, but if they did have it, their G value, the acceleration is so high, they would probably be all dwarves or whatever they could be, that they would not grow as tall. So that's something that needs to be taken into account. All right, let's see a quick problem on where this is used derivatives in real life. You can use this as well in your everyday life if you can model it. A farmer has a 800 fence, okay, meters of fencing, and he wants to enclose a field So basically this is the field, okay? And one side of the field is against a road. So I guess there's a road here. So this has already been fenced. So he doesn't need to worry about fencing that. You understand?
Mm-hmm.
But he does need to fence these 3 sides. He wants to maximize the area. So the question is, how much should this be? Like he has 800. He could do like, I don't know, like 200, 200, 400, right? That'd be one particular option. Or he could do 209, 199, 400. That could be another one. As you can see, there's gonna be a lot of permutations here. But we don't care about permutations. I mean, we don't want that because we don't want to be doing like 10,000 iterations of the same thing. We're going to deduce this mathematically using derivatives exactly what's going to give him the maximum area. Because at the maximum area, what do we know? The slope is going to be 0, right? And the
Mm-hmm.
maximum area just means a maximum point. We know for a fact the slope is going to be 0. So let's use something to model this. I'm going to let this side be, I don't know, like length. They're equal, right? And let's say this is the width. What is the perimeter of this field as it is? Perimeter is sum of all the relevant sides, okay?
Mm-hmm.
Perimeter just means we have 800 meters. That's what that means. We have 800 meters that we can use on these 3 sides. And we know those 3 sides, if we add them up, you get length plus width plus length. So this is how you get an equation. 2L plus W is 800. Do you see that?
Mm-hmm.
That means W is 800 minus 2L. Cool?
Uh-huh.
All right, I'm gonna need your help here. It's pretty simple. What's the area of this field in terms of W and L? It's a rectangle.
W times L.
Yeah, W times L. And now we know W is 800 minus 2L, right?
Mm-hmm.
Times L. If we FOIL it, what do we get? If we open that bracket,
800L minus
minus what?
0.
2L squared. Yeah,
Mm-hmm.
2L squared. So there we go. That's all we needed to do. We have a function of area, which is a negative parabola that has a y-intercept of 800, and we know it's opening upside down because of the negative 2L squared. So it looks like this. And the equation for this, which we just found, 800 minus 2L squared. How do we find this? That thing there, right? That's when the slope is 0. Do you agree?
Mm-hmm.
So this is area. So let's find the slope function, which will be A prime. What will A prime be? If A is 800L minus 2L squared, what's A prime?
800 minus 4L.
Yes, 800 minus 4L. And what's the slope here?
0.
0. So this is going to be equal to 0. So that means 4L is going to be 800. L is 8 over 4, 200. There you go. L needs to be 200. That means our width is going to be 800. Okay, actually, we somehow fluked the answer here. 800 minus 400, 400. So the width should be 400. This one should be 400. And the L's should be 200, 200. And there's a road here. That'll give him the maximum amount of area using 800 meters of fencing. Cool.
Uh-huh.
So there you go. That's like a real life application of this.
What if you had to find the minimum amount of area?
The minimum amount of area would be a straight line. Minimum is 0, right?
Mm-hmm.
So basically it's counterintuitive, but the minimum amount of area would be, let's say this is the road. You just do this. You never close the rectangle. You use 800 like this.
Okay.
It's counterintuitive. But yeah, that's how you do it. Did they get that? Yeah, 200, 400. There we go. Yes. Okay, the other question is gonna take a while. Let's do one of these quickly. I don't want to do that. 7/3. Let's do 10. Do you like curling?
So I've never tried curling.
Yeah, I think it's weird. It's a weird sport. Um, okay, so again, position. How far does a stone travel before it stops? Ooh, interesting. What does that mean? Well, how would you approach this? How far does it travel before it stops? That means the velocity is gonna be 0, right?
Mm-hmm.
When it stops, the velocity will be 0. So what you do is you find s prime of t, which will be what? Find the derivative of that function up there. Well, 12t is just going to be 12, right?
Uh-huh.
Minus, bring the 3/2 down, and then subtract 1. 1/2 minus 1 is just a half, like that. So you can clean this up a bit. It's going to be 12 minus 12/6 square root of t. There we go. That's the velocity function. Set it equal to 0, because that's when it stops. And let's find time. How do we solve for t here?
You subtract 12?
Yeah, so 6 root t is going to be 12, or minus 6 root this. So root t is 2. So what's t if root t is 2? T is square both sides to get rid of the square root. So t would be 4 seconds. So how long is it moving? It's moving for 4 seconds. How far does it travel? We want to plug 4 back in here. So 12 times 4 minus 4 times 4 to the 3/2. So 48 minus 4 times 4 to the power of 3 divided by 2, 16 meters. So it travels for 16 meters and it's moving for 4 seconds. And we are done. See, it's pretty simple, right? Just find the first derivative, set it equal to 0. That kind of solves almost every problem when it comes to derivatives. Okay, cool. Let's stop there for today.
All right, thank you.